Hello, Charger family. This is Mrs. Boyd at Mrs. Boyd's Math Room. Thanks for joining me today. We're going to talk about SSS and SAS congruence. It looks like S and SAS, but it's really SSS and SAS all separate. So first, let's start with the SSS congruence. Triangles can be proven congruent when all of the sides of one triangle are congruent to all of the sides of a second triangle. So if we have triangle ABC and triangle DEF, if AB and EF are congruent, and BC and FD are congruent, and CA and DE are congruent, then these are congruent triangles. And we show that by writing triangle ABC is congruent to triangle DEF. I hope you caught my mistake. Totally did it wrong. It should be triangle EFD. All right, so we haven't really done a bunch of proofs except for Uno. So we're going to try this out and see how it goes. We've got triangle ABC and triangle XZY, and we want to prove that they are congruent. So we have segment AB is congruent to XZ, BC is congruent to ZY, and segment AC is congruent to segment XY because it's given. So now we want to say, why is it that we can say that ABC and XYZ are congruent? All we have to write is SSS, side, side, side congruence. Let's do another one. We have segment JK is congruent to segment LM. Segment JM is congruent to segment LK because those are given. Well, we know that the only side that we haven't talked about yet is this side JL. So JL is the same side on each triangle. So JLM and JLK make the same triangle, right? So all we have to write here is segment JL is congruent to segment JL because of a little thing we call the reflexive property. That same line is used in two triangles. It's the reflexive property. Then finally, we have JML is congruent to triangle LKJ because of side, side, side congruence. With me so far? To do a little bit more exciting, we have segment EF is congruent to GF, and H is the midpoint of segment EG because it's given. So we know that the same thing we had in the last set of triangles. We've got this segment FJ that's shared by both triangles. So we can say that segment FH is congruent to segment FH because of the reflexive property. Next little piece that we need to look at is, if we want to use side, side, side again, which we do, is EH and GH. We need to prove that EH and GH are congruent, and we can do that because, let's go ahead and write our statement down here. EH is congruent to segment GH because the definition of midpoint. In our given statement, it says that H is the midpoint of EG. Well, that means that EH and GH are the same length. So last but not least, our final piece that we need to prove is that triangle EFH is congruent to triangle GFH, and we use the side, side, side congruence to do just that. All right, hope you are hanging with me in the understanding department. Let's go on to this last one. We have segment QR is congruent to segment QT. Segment QS bisects RT, and that's a given. So let's look at the things that we already know how to do. We already know how to deal with QS, this segment in between two triangles, shared by two triangles. So let's do that. Segment QS is congruent to segment QS because of the reflexive property. We also know a little bit of something about what's going on with RS and TS, because in our given statement, it said QS bisects RT. That means that ST and SR are the same length. So RS is congruent to TS. It's the definition of a segment bisector. Last but not least, QRS is congruent to TQS because of side, side, side congruence. We've proved that all three sides are congruent, so that means the triangles are congruent. I know this is different than anything we've done before, but you can totally do it. Stay with me. Let's move on to the back here. We're going to look at side, angle side now. It's a lot the same, except for it says triangles can be proven congruent when two sides and the included angle are congruent to two sides and the included angle. The included angle means the angle between the two sides, the angle that's formed when the two sides touch. So we have AB is congruent to DF, and I know BC is congruent to FD. And I'm also going to tell you that angle B is congruent to angle F. So we have a side, an angle, and a side in that order. These two side lengths form this angle. Side, side, and angle. So I know that triangle ABC is congruent to triangle EFD because of the side, angle, side congruence. Let's do a couple of proofs for this one and get used to that. We have given that C is the midpoint of line AD and C is the midpoint of segment BE. That's given. Well, what else do we know? We know that segment BC, if C is the midpoint, then BC and CE have to be equivalent. They have to be congruent. We also know that AC and CD have to be congruent because it's the midpoint of that line as well. And that's because of the definition of midpoint. Just like the ones on the front side. Now, we have two sides and we need the included angle. So there's a word for what these angles are called, BCA and BCE, or actually BECD. These are called vertical angles. So we know that angle BCA is congruent to angle ECD because of the vertical, I'm going to abbreviate here, angles theorem. That says vertical angles are congruent. So now we have on each triangle a side, an angle, and a side, an angle, and a side that are all congruent. So we know that triangle ABC is congruent to DEC because of the side, angle, side congruence. Let's look at another one, another proof. We are given segment GH is congruent to segment FJ. We're also given segment GH is parallel to segment FJ. That's what these arrows mean on our two lines. If these arrows are found on these lines that are across from each other, that means they're parallel. So GH and FJ are congruent, and GH and FJ are parallel. So let's see what else we know. Well, just like before, we can say a lot about segment GJ. We can say that GJ is congruent to segment GJ because of the reflexive property. We're used to that one. Now we need an included angle. Well, we've talked about this quite a bit. Let's take angle G. If GH and FJ are parallel lines and GJ is a transversal, we know that angle HGJ is congruent to angle FJG because they are alternate interior angles. It's the alternate interior angle theorem. So we have a side, angle, side, side, angle, side. So that means we know that triangle GHJ is congruent to triangle JFG by the side, angle, side congruence. Two more on the home stretch. Okay, we are given in this set of triangles, segment KN is congruent to segment LN, and segment KL is perpendicular to segment MN. So let's look at what we know. We know that we know all about line segment MN, but this space is too big for that. So let's look at if KL is a line and MNL is a right angle, that means KNM is also a right angle. So we can say that angle KNM and angle LNM are right angles because perpendicular lines form right angles. All right, so we know those angles are equivalent, are congruent. We know that KN and LN are congruent. All we need now is NM. Oh, no, wait, just kidding. So we know that KNM and LNM are right angles. Now we need to say, we haven't said they were congruent yet, so now we need to say that KNM is congruent to angle LNM because all right angles are congruent. Last but not least, we know all about line segment NM being congruent to line segment NM because of the reflexive property. And KNM is congruent to triangle LNM because of side angle side congruence. Oh my gosh, just one more. And we've done it. All right, we've got line segment QS bisects angle RQT, and segment QR is congruent to segment QT. Let's see what else we need to know. Well, we know that if QS bisects angle RQT, we know that if it bisects it, it splits it in half exactly. So we know that angle RQS is congruent to angle TQS because it's the definition of an angle bisector. That's a T. Holy cow. So if you want to use some abbreviations on these, you totally can. Do whatever makes sense to you. So we know these angles are congruent. So now we've got side RQ is congruent to side TQ, angle Q and angle Q. Now we need QS, and we know how to write that. Segment QS is congruent to segment QS because of the reflexive property. So triangle QRS is congruent to triangle TQS because of side angle side congruence. I hope this makes some sense. Along with the proof, we're going to get lots of practice describing things, and I'll give you some handy dandy shortcuts and reference tables to use. If you have any questions, please come and find me. You know how to reach me, and I hope to see you very soon.